So we are on 8.3. This is our last section before the test. So testing a claim about a mean. 8.2 was about testing a claim about a proportion. We do have this now printed out, hopefully. This will help you as you make a conclusion about the claim. So if it's a null hypothesis, the claim is a null. That's whenever you have the claim is, or the HA is where something, let's say P, doesn't equal something, some number, let's say 0.2. So you'll use this one whenever it's a two-tailed. Because the claim is your null, because the null is always the equal to. So for your alternative, you'd say not equal to. Whenever it's an alternative hypothesis, the claim is found as your alternative hypothesis. So like HA is P is less than 0.3, or another one would be mu is greater than 0.2. That should be a mu. Sorry, it looks bad. So that's the mean. So this is proportion, this is mean. So these are either left or right-tailed. This will help you come up with your conclusion. So we're going to use this today. We also need to have out 8.1 because it's really helpful to go back to this. If you want to do kind of a conclusion here, you always do p-value, and then you compare it to your significance level. If it's less than or equal to, then that means we are going to reject the null. So this is coming from 7. If it's greater than, then it's going to be fail to reject the null. So this is kind of like your cheat sheet for making conclusions, making decisions and making conclusions on your hypothesis testing. So you'll reject the null when p-value is less than the significance. When p-value is greater than significance, you fail to reject the null. And then this decides what you do about your claim. So let's go on into 8.3. Our objective is use a formal hypothesis test to test a claim about a population mean when the standard deviation is unknown. So our notation, n is our sample size. X bar is our sample mean. S is our sample standard deviation. And then mu, mu x bar, or just mu, is going to be our population mean that comes from our claim. So used in our hypothesis, H naught and H alt. So our requirements are that it's a sample observation of simple random sample. Either one or both conditions are met. Either the population is normally distributed or we have a sample size that's greater than 30. Our test statistic is found by T, which is called our student T distribution. And that's x bar minus mu x bar over s over square root of n. Our critical values, they are going to be from the A3 table. Just remember, degrees of freedom means our sample size minus 1. And then our p-values, we can use technology. So we have the technology, I think it's called t-distribution. We're going to go over it in a minute. T-test. And we can also use normal CDF. Not normal, it's called TCDF. So I'll talk to you about that one. Because it's not a normal, it's a t-distribution, so we're going to use TCDF. So we use t whenever we're talking about means. And when we're talking about proportions, we're using the z-score. Okay, so the requirement is that it's either already normal or n is greater than 30. If the original population is not itself normally in distribution, then it must have sample size greater than 30. Sample size of 15 and 30 are sufficient if population has a distribution that's close to normal. The properties of student t-distribution. So look at this chart. This shows you what each of them look like. So standard normal is this z. So it's the one that actually has the bell curve. It goes up higher. T-distribution with n close to 30 is rounded a little bit more. And then if n is smaller than 30, it looks a lot like a quadratic. It just looks like a mountain. It's not real steep at all. So it's different for different sample sizes. Normal, it's always the same. It always looks the same, bell shape and symmetric, but t-distribution is different for different sample sizes. It has a general bell shape, but it's wider. So see how this is pretty narrow up here? This one's a little bit wider, and that reflects greater variability. Your mean for the t-distribution is t equals 0. Standard deviation varies with sample size, but it's definitely greater than 1 because of the variation. As n gets larger, then the t-distribution becomes closer and closer to a standard normal. So that's why we're able to approximate with a standard normal when n is greater than 30. We just have a couple of examples. Example 1, use technology to find the p-value for the hypothesis test described below. The claim is for a smartphone carrier's data speeds at airports. The mean is 17 megabytes per second. Sample size, n equals 24. Test statistic is t equals 2.403. So we are going to identify the p-value and then be able to just look at our p-value and we can compare it to a significance level if we had one. So this is our claim. So let's identify our H naught and H alt. So this claim has that it equals 17. So that's actually going to go for not, because not hypothesis is always equal. So mu equals 17. And it could be mu x bar, like that. or we can just leave it like mu. That's an X with a bar on top as our subscript. And so our alt, whenever our claim is equal, is that it's not equal to 17. So when it's not equal, this is a two-tailed test. Two-tailed. So n equals 24. So what are the degrees of freedom? 23, because you just take one away. It already gave us what t was, 2.403. So on our t distribution, something like that, we have t is at, so 0 would be right in the middle. This is a two-tailed test. So I'm going to put a mark at 2.403 and another mark at negative 2.403 since it's a two-tailed test. So the two tails would be these. So we need to find the p-value, probability, which of course goes along with area under the curve for those two sections. So we're going to use our technology. So calculator. We're going to do a distribution. This is the TCDF. So we're going to do second vars and then do the TCDF. Clear. So our lower would be negative 2.403, and our upper would be 2.403. And what this comes up with is the area between them. But we want the opposite of that. We want the complement. So when we finish this, this is going to give us the area here. So we're going to have to subtract from 1 to find the complement, which would be over here. Subtract from 1. So our degrees of freedom is 23. So if you want to write that down so you know how to do it on your assignment, this might be helpful. So go ahead and paste it in. So this is how it looks whenever it pastes it in. So it comes out to be 0.975, I guess 3. We go 3 decimal places. But we want the complement because that's what this is. So we're going to do 1 minus that. In the calculator, I can just do 1 minus and then come up here, select it, and bring it down. Push enter. So that would be considered our p-value. So we can find our p-value just knowing our claim, how many are in the sample size, and then our t statistic, test statistic. Okay, let's go to the next one. The display provided from technology available below shows from using data from a smartphone carrier at an airport to test the claim that they are from a population having a mean less than. We're going to change this because I forgot to include the display. So let's change this to 5, and I'm going to give you the display. Conduct the hypothesis test using these results. Use a significance level of 0.05. Identify the null and alternative hypotheses. Test statistic, p-value, and state the final conclusion. So our t-test results are these. This is what would come out on the calculator. It's just I forgot to copy it over. So let's identify the null and alternate hypothesis. So our null is always that it equals that claim. So mu equals 5. Our alternative is what they actually say what the claim is. So mu is less than 5. Our test statistic would be t. And guess what? I forgot to write that. Sorry. That would go actually first. Oh, right in between here is where it falls. So t is our test statistic, negative 2.21. Let's just go 2 decimal places. P-value is right here, is P. So in order to come up with a conclusion, we're going to compare the p-value to our significance level. Here's our significance level. So p-value, significance. Looks like our p-value is less than our significance. So if we look here, less than means we're going to reject the null. Conclusion, reject null. So what does that mean about the claim? So if we look here, we are in it's a less than, so we're in the left tail. So if we reject the null, there is sufficient evidence to support the claim. That the samples from a population mean less than 6 megabytes per second. See how helpful this chart is? Okay, the next one, I actually copied and pasted this twice. So there's really not enough room on this one. So this is the actual example with everything listed out, what you need to find. So listed below are the lead concentrations measured in different traditional medicines. Use a 0.10 significant level to test the claim that the mean lead concentration for all such medicines is less than 14. Assume the sample is a simple random sample. Okay, so we need to identify our null and alt. So let's see. It says the claim is that the mean lead concentration is less than 14. So our null is that it equals 14, and our alternative is that it's less than 14. We need to identify the test statistic. Well, we just have data right now. So we're going to have to use this data, and we can use the t-test. So we'll go to stat, and then L1, put the data in. Then we're going to go to stat and do t-test. And make sure it's under data. So from this data, if we were going to do this by hand, we'd have to find X bar and our standard deviation, which we can do that. And then we'd have to use the formula for the test statistic, which we had that over here. No, on that page, sorry. On this page for 8.3, the first page of 8.3. And then you could find your p-value from there. Let's go ahead and go to stat and let's put our data in to L1. So this is our data. Those are the amount of lead concentration in traditional medicines. Make sure you double check your numbers. Okay. Hopefully you have your data in. Okay, so now we'll go to test, stat, t-test, data. And it's coming from the data. H naught is our hypothesis mean, our population mean that we're testing, which is 14. List is an L1, frequency is 1. We're looking at it being less than. It's a left-held. So then we'll calculate. Did you get the same thing? Did you get the same thing? Okay. All right. So let's write down what we got. So our test statistic is T, negative 2.015. Our p-value, 0.037. So what we would need to do is compare our p-value to our significance level. I'm going to go ahead and just add an extra 0 on there so I can compare it a little easier. What does this mean? What symbol do I put there? Less than? So our p-value is less than. So what does that mean? Less than means we're going to reject the null. So what does that mean about our claim? So if we have a left tail because it's a less than, we reject the null. That means there is sufficient evidence to support the claim. So there is sufficient evidence to conclude that the mean lead concentration for all medicines is less than 14. So this is the math to back up what our conclusion would be. Look at all these numbers. Do you notice that they're all less than 14 except for one? No, 3. They're 3. So with a significance level of 0.10, we can say that there's sufficient evidence to conclude that the mean is less than 14. Okay, so that is it for 8.3.
It can last at least approximately 5 weeks. And I don't think it's fallen out yet.